Ladies and gentlemen, good morning. I'm really pleased that I can see you, and it's a great pleasure to see that many of you on this event of the Slovak hydrogen ecosystem. And today's venue, compared to the previous ones that were dealing with the other aspects of the ecosystem, how the hydrogen works in many of the branches of society and economy, how the environment should be improved in legislation way or others. These were interesting, but these rather were quite vague and general. What would be good to do is to take a look at hydrogen as a practice form of energy. And it's a very good proof how to say that these are not theoretical theses of officials or academics or somebody else, but these are very practical things that could really work. So the subject matter of today's event is hydrogen mobility, and we will be dealing with a project that is financed by the European Commission, and the hydrogen mobility is being presented by the project of Tomark Proton Company. Due to the fact that we also have to give you some introduction how these projects work or what is their meaning for the ecosystem from the innovation point of view, at this point I would like to welcome you, and I would like to invite the general manager of the section of the strategy of Ministry of Economy, Ms. Augusti, who will be speaking about these things. Thank you very much. I didn't know that I'm supposed to pass over these information. Thank you very much for the invitation. This really makes me happy, and I see hope that we have many people in Slovakia with great dreams and ambitions. On the other hand, it's really difficult because we are in the phase of the so-called kick-off and visions which are being drawn and today will be presented to us. Another phase is still ahead, and you know best yourselves that another demanding phase will be to create a prototype, and also the scale up will be very demanding. Many times we hear that the scaling of the problem in Slovakia is difficult to get over the barriers. But when I see Mr. Sedlak from the Tomark company, this gives me hope that it could be really successful. And I would like to wish you that in next year we will be opening a conference with a prototype, and hopefully I will be also invited to the scaling of the project. Hopefully we will see who will buy this project, but I am keeping my fingers crossed with this project. The objective of projects is to create a great team, create something real, and to make it happen. So I'm really very happy that I can be a part of it, and I will pass the floor to the host. Thank you very much for the kind words. You know Professor Sinai, he doesn't have to be introduced because everybody who's dealing with hydrogen know him. But I would like to invite him to present. Ladies and gentlemen, it's really great pleasure for me that I can be here today with you at the kick-off meeting. Everybody knows what kick-off meetings are about. It's a great pleasure for me and honor to invite you here. And the reason is very simple. Slovakia, from the very beginnings of the calls for proposals, we had many active and also sleeping stakeholders. Everybody thought if there is a hydrogen project, we should start with it. But when the page is being turned at the applications, but it seems that the effort was a little bit more than the capabilities. But our today's project is among one of the three which were successfully elaborated. And when it was shown to the bureaucrats in Brussels, they had to say, this is a good project. So we have NAFTA projects. The second project is the Tomark projects, where I can tell you that we will be checking you in the upcoming times, but to check you, how are you spending the money and what is your vision, how to deal with it. I'm very happy that I will be able to hear something interesting today. Tomark company is from Prešov. I was the previous dean of the Technical University of Prešov, therefore this company is very close to me and also the other projects. But this company, when you enter this company, you will see that they are earning the money with more simple works like welding of trucks. But then when the other doors are being opened to you and you can see really very clear facility, there are airplanes which are being assembled, you have to see it to believe. When I visited the company with the State Secretary Hodoshi, we were sure that this company really has the potential. Just like the Madame General Director already said, I was fascinated, but I'm not keen to use the word fascinated, but when we take a look at the companies which you have already contacted, you have groups for designing, for drivetrain. I was counting it in your material and I sent it to Katka, and when it comes to the collaborating institutions, I wasn't even counting it. And I told myself how Mr. Sedlak wants to coordinate all this. But today we will see it. I'm very happy that we are in this phase of the project, but I'm a little bit concerned. It's really such a large of a project that unless we secure the financing of this project all the way to the end, it could happen that we will be forced to ask our partners to finance this project. But I strongly believe that we will be able to manage. This is what we are here for, and we have this trinity of the State Secretary Hodoshi, General Manager Kautka Augustini, and me at the end. We are really keeping our fingers crossed. We are looking forward to see what you have already managed. But this is not only about the airplane, which is a good thing. Maybe it will be done, maybe it will not be done. But one of the main objectives of this project is the production, testing of composite vessels for aerospace. And this is all the way from Airbus to other producers. If we would be able to do this, if our composite vessels will be produced in Prešov, and maybe they will end up in Hamburg or Hanover, and we will create a monopoly out of it. I'm keeping my fingers crossed. I'm wishing you all the best. And I'm really very pleased that Mrs. Augustini took her time to come here. We are also giving them the information about the hydrogen, and I can tell you that I haven't had such an eager student when it comes to the hydrogen in Madame State Secretary. I haven't had such a person. So Katka, thank you very much again. I would like to ask you to work on this project all the way to the end, because all these people who are being presented here today, it should be done for them. So thank you very much, and I'm really looking forward to see the presentation. Thank you very much. I think that if you have the feeling that we have been speaking for a long time and we didn't see anything yet, maybe this is the mistake of the host. But I think, in my personal opinion, that time is up to also to present the person who is behind this project, and nobody else should be presenting the project than the person who created it. So let me pass the floor to Mr. Martin Sedlak, who is not only the CEO of Tomark Proton, but last but not least is the leader of the IPC project. So we don't have anybody else who could be presenting it. So let me pass the floor to Mr. Sedlak. Thank you very much.
Thank you very much. I would like to greet the professor as well as the general director, really encouraging words. And we have the pressure of responsibility, but we have had some space to get used to that. We got the idea of the project together with the Tomcos 4 years ago, roughly. And at that time, we were thinking about where the aircraft industry is going. I will start the presentation now. As you know, we are pilots and designers. We are standing with our feet firmly on the earth. Our heads are in the sky. We are looking to the horizon. In aircraft industry, everything takes maybe 5 to 10 years, a long time. So you have to think carefully about further steps, about what you will take as the next step. Enthusiasm and courage on the one hand, but also you have to think about that carefully. Mr. Tomko said several years ago, shouldn't we build a plane? Well, and we managed. We've created that. We certified it. We service that and sell them. And those planes were so successful that we continued with Skyper 9. But as pilots, we are looking to the future. We started to think about how a plane of the future could look to be economical but ecological at the same time. Are we able to fly with the batteries far enough? Can we carry enough? How long it takes to charge them? Is there another alternative? When we under certain circumstances, it could be combined with hydrogen. But to build something like VTOL, hydrogen plane is economically really demanding a task, and we could break our legs on that. That's the reason why we thought about a grant. And IPCEI was the answer to that. IPCEI, a very complicated abbreviation about joint projects of common interest, the European interest. But it was not just our interest, but also interest of other companies. Therefore, we had a big fight. The European Commission with the Research Center, through many iterations, evaluated us economically, ecologically, and technical potential. After roughly 4 years, we got to top 10 companies that list dealing with hydrogen. We are not alone here. We have direct partners. One of those is BMW, German company, or another company with 100 history, Messer, French company, Evel, or Estonian Skeleton. So we have partners abroad, but also here in mobility, innovation and production. Slovenská pokroková spoločnosť is from our home country. So we have more than 20 partners, direct partners, but we are not ending here. We cooperate with universities. Gradually, we will start our cooperation at least with 9 other partners, and we think there will be more of them. We started the project in October 2024 as scheduled. It's interesting, out of these 10 companies, only 3 were able to start on time. And that was due to a good cooperation with the Ministry of Economy. Our budget is more than 60 million euro. We will work until 2030. We are not working just on the research and innovation, but we are dealing with the first market introduction. Beyond 2030, we will start with a serial production. We will start with something real. We won't stay just on paper. Our tasks are divided into two parts. Now we are in the initiation phase, in the kickoff phase. So we are thinking about what the plane on a hydrogen of VTOL type should look like, where the crew, where the pilot engine and everything should be. And these are questions that will be answered by my colleagues during today's event. So we are thinking about our concept. Therefore, in 2026, we will build Iron Bed, which is the testing laboratory on Earth. So before we start flying, we will test those systems on Earth to be sure. Parallel to that, the second task is development of high-pressure composite vessels. That won't be developed just for internal usage, but to implement that, deploy it for other transport, for its stable storage. So we are thinking about the shape. Should be cylindrical? Should it be oval, or with what materials should we work? 350 or 700 bar. What should the first lab look like, or the machine equipment, so that our ideas are materialized? When we started with the project, one of the frequent tasks was, shall we find enough experts? Do we have capacities, sufficient capacities? A sad answer, we don't, because our experts have gone away to abroad, but the grant is, however, here. You have an interesting project, and through that, we were able to attract the experts back to Slovakia. And today, thanks to this grant, this is the added value that is established here. Thanks to this grant, we can increase investments into innovation and thus bringing Slovakia upwards. So this is also our objective. Thank you for your attention. And now I will pass the floor again to our moderator. Thank you very much. This is the phase when about a very complicated, comprehensive project. I didn't know that we can talk about that so simply, but I think the words said how much work is behind that. I think in a similar spirit, further presentations will follow, as Mr. Sedlak has outlined. So to speak about the project in detail, so series of presentations will follow where different experts engaged in the project will talk about aspects, how it worked, as at the end, this is just an organizational remark, at the end of the block, we will have some space for your questions. Feel free to collect them, maybe put them down. And we've seen also the QR code Slido. QR code, you can see that on the monitor. And if you have a question, feel free to write it down. Also, maybe with the address, so to whom you direct the question. And after this block, all speakers will be available to you to answer all your questions. And now, Marian Takac will talk about... No? Sorry. So Tomáš Uhrík will speak first, who will talk about the technical preparedness of the project, and he will talk about how far the project got. Thank you.
Good morning. I will start my presentation. Okay, this is how it should look. So this is a presentation, just like it was already said, about the technological preparedness of the topics we have been dealing with. And the objective of this workshop is to present the challenges which we have set at the very beginning of our project, which deals with hydrogen power. And at the same time, we would like to show you the methodologies which we use when dealing with these challenges. This meeting is considered as a unique opportunity how to deepen the collaboration with all the stakeholders, with the industry, and with all the scientific institutions who have been supporting us for a long time. We believe that a mutual dialogue and our discussion could help us to create new synergies with a permanent cumulative effect during our scientific and research work. To be more precise, this presentation shows the basic topics of our research from the point of view of their technical preparedness and where we want to get during the project. As it was already mentioned by Mr. Sedlak, we have two main topics: the storage of hydrogen and research and development of airplanes that would be able to land and start vertically. Basically, as already mentioned, we are searching for a certified, fully used solution which would be capable to be used in transportation vehicles, be it airplanes or also in cars. When it comes to airplanes, we would like to move the research from the level 2 to the level 7, which already has to do with the testing of pre-production prototype in real-time conditions. And both these topics are interconnected into a single topic, which we call ecosystem of hydrogen mobility. And in this project, we would like to create a peninsula or an island which would be connected to the Slovak environment, and therefore we want to be creating a whole ecosystem from the production to the storage of hydrogen all the way to the operations of particular facilities or vehicles, be it airplanes or buses. Using this ecosystem, we would like to get to the level 4, which is already testing of the system in a smaller scale. Before the colleagues will be presenting you more complex topics, I would like to also speak about the main historical consequences. We'll be speaking about the VTOL, which is a vertically landing and starting airplane. First airplane of such a kind is embarked to Mr. Da Vinci. I would like to start my presentation, but this technological preparedness was prepared for such a solution at the beginning of 19th century, and during this time such a facility was tested. It could be called coaxial helicopter, which was also studied by Mr. Jan Bahil, who carried out the first flights around 120 years ago. And the longest flight was 1,500 meters. So he created an airplane heavier than air, which was able to start vertically. Another project I would like to show you because there is a lot to be speaking about, is the airplane of Mr. Petrocci, and he managed to get finances from authorities, and he created a wider team dealing at the beginning of the 20th century with the research of VTOL airplanes. For example, with his colleagues, he created several patents and prototypes. As you can see on the picture, this is a quadrocopter which had the propellers aligned in one line. So here you can see basically the four propellers. Colleagues were basically bypassing certain research problems with the fact that they anchored the airplane, because the maneuverability of such airplanes was really very difficult, and the solution basically for their problems we only discovered at the beginning of the 21st century. Here you can see certain prototypes of Mr. Petrozzi and his colleagues. These airplanes were called PKZ-1 and PKZ-2. As you can see on the picture, they were hovering at a height of 50 meters. Back then, they were testing on the Schwechat airport, which was back then called Fischament. Here you can see the electric engine, and we basically, due to the fact that it was using an electric motor, consider it the first VTOL airplane. The engine was, for the project, was delivered by Ferdinand Pouček, who was working for the company back then. Here you can see the prototype of the PKZ airplane, which was hovering at the height of 50 meters. So basically we have a history of such airplanes in the Central European region. When it comes to the hydrogen itself, practically at the same time as hydrogen was given its name, we were able to generate burning nitrogen, and Jean-Pierre Pilate de Rosière created an airplane which was basically a combination of the airplane and a balloon, and it was based on the hydrostatic physics laws. The renowned Zeppelins were also used as airships. And we are at the moment thinking about using the same technology with more ecological gases, just like the hydrogen, because it's more ecological, and this hydrogen would be also used to drive the Zeppelin. So these airplanes, which have vertical air starting and landing, actually hydrogen is helping us using fuel cells. This could help the whole drivetrain cycle, which could be really more ecological using hydrogen. Another famous milestone is the deployment of hydrogen in airplanes, was the Lockheed CL-400 Sun-10 airplane, which was the first airplane using liquid hydrogen for its power. There was a really great work done when it comes to the infrastructure of the hydrogen, but unfortunately they were missing finances, and the next airplanes were not developed. When it comes to the hydrogen, when it comes to the hydrogen infrastructure, it was used in the space program of Apollo and Gemini. I didn't show you the photo of Theodor von Karman from Budapest, and also Mr. Hermann Obert, one of the three founders of space program globally, which was also born in Austro-Hungary. So I wanted to show you these pictures and share these photographs, because these are really the people behind the space program, and they actually helped us to move forward. When it comes to spillover or the overlapping of space program, helped us to develop a hydrogen fuel cell. So this is the polymer-based membrane, which is also the called proton exchange membrane. And for the first time, such a fuel cell was used in the Gemini airplane. It was not used for the drivetrain of this vehicle, but as an energetic resource for the board devices. And this hydrogen was also used as the primary fuel, because we just hydrogen is considered one of the best fuels there is. So these were the very beginnings of fuel cells powered by hydrogen. And when we speak about the fuel cells itself, these are the fuel cells we would like to use in our project. And the reason is that the level of their preparedness from the technological point of view is far ahead. The others are at the level of 2 or 3, which means the specification of a concept or lab tests. And what is the fuel cell itself? Here, basically you can see the structure of the fuel cell, and when we speak about the fuel cell, actually we mean the whole system. This is the heart of the system. Here you can see the real state of play. It's basically a stash of fuel cells which create electricity, changing the chemical reaction of hydrogen and oxygen. Just let me explain you briefly. Each of these fuel cells is composed of these distribution parts. Here you can see the polymer membrane, which was developed at the end of 60s and 70s. And the development of it was related to the space program. And here you can see the distribution boards of the fuel cells. Here you can see the hydrogen from one side, oxygen from the other side, and using a catalyst, there is a decay of the hydrogen into protons and electrons, and here it is mixed. At the same time, heat and water is being produced. And here you can see the production of electricity. So basically this is the brief description of what happens in these hydrogen fuel cells. There are many different types of these fuel cells, and in collaboration with our partners we're trying to find the most proper one. When it comes to the storage of hydrogen, my colleague Klaus Ritter will be speaking later on about these, but we are still considering the options how to storage hydrogen. One of the most interesting ways for us is the metal hydride way of storage, And together in collaboration with universities, we are preparing a storage tank where there is a metal hydride powder, and colleagues which deal with the hydrogen mobility know it. From time to time, there are certain news that there is a break in the development of the storage of hydrogen this way. We have also considered a tank for this liquid hydrogen, but due to the fact that the hydrogen has to be stored in the temperature of minus 250 degrees, we left this thinking, and we will be dealing with the compressed gaseous hydrogen. So this is our way how we want to store the hydrogen. So definitely we will have the vessels of the fourth type, but my colleagues will tell you more later on. When it comes to the deployment of these fuel cells and tanks in airplanes, certain partners and stakeholders of our projects are already experienced, because they already have experience with our projects which deal with fuel cells. These were of 20 to 40 kilowatts of performance. The first fuel cells were used in Boeing airplanes in 2008. And here you can see the first sets of flights which were already powered by hydrogen. So we already have deployment experience. And when it comes to the deployment of hydrogen fuel cells for the flights, this is actually happening. The research is ongoing, and here you can see the first projects which are already powered by hydrogen. Here you can see on the left hand side of the slide, here you can see Joby, and on the right hand side you can see the retrofit helicopter using hydrogen power. None of these were built for use of hydrogen fuel cells from the very beginning. So this is why it could bring us new options and new possibilities to improve the deployment of these fuel cells. And in this project, we would like to search for the most appropriate version of such an airplane which would be using the fuel cell. And the main challenges we are facing are the following. It's the density of the fuel cells. At the moment, the deployable fuel cells have 200 kilograms, and with our partners, we would like to produce 300 kilowatt at 300 kilograms, which is higher density. I don't want to be even calculating the previous density. You can do it yourselves. And when it comes to the tanks for hydrogen, we would like to achieve an innovative solution, which would be a revolutionary solution for us. And this has to do with the optimization of the weight and security at the same time. Nowadays, we are speaking about the volumetric ratio, which is at the level of 6%. So the tank, which has 600 kilos, can store 6 kilowatts of energy. So we would like to be storing at least 10 kilograms of hydrogen. As I can see, Klaus, 10 is the minimum. So 10% compared to the previous 6% ratio. And last but not least, we would like to use this opportunity to harmonize the creation of the legislation for the use of hydrogen for the use in airplanes. And basically,
we would like to create legislation which allow us to put such hydrogen airplanes into operation. And to sum it up, we would like to be trying, as I already mentioned, within our ecosystem, which is not only focused on one part of it, but we would like to be dealing with all of the other parts simultaneously. So these are the challenges which we have been facing, and we would like to continue to describe these topics in upcoming presentations. So I would like to thank you, all of you here, for the trust and your support, and we are really looking forward to see the further development of our project. Thank you very much.
Thank you very much. And well, it was extremely interesting to see how well we can build on something that was created several years ago with its usage today and development also of flying machines. Before, someone of us has seen a hydrogen flying device, so we've become beneficiaries of many times unwanted but wrong information about how hydrogen is dangerous, which were based on something that well, maybe something from defense industry, but in many cases, well, it's quite obvious that it's not like that, but it's presented in different ways. What is, however, important is that an important part of the project, as of Vito from Temark, is the risks and safety dangers, as well as legislation that ensures that with application of hydrogen in VTOL aircraft, these requirements are secured. This topic will be described by Mr. Marian Takac. Thank you for the floor. I'll start the presentation first. I've managed. So, thanks for the floor, ladies and gentlemen. I would like to continue. As Tomáš Uhrik said, just briefly, I would like to say something about the risks of well, safety risks and legislation, which is not existent in terms of hydrogen source. So first, we will sum up what we will talk about. In the introduction, we will talk about the basic challenges regarding integration of the source into VTOL. We will repeat the crucial key things that endanger the aircrafts which we have to fight with, and also the systemic challenges. Then we will talk about legislative requirements and standards, the current status of the legislation for hydrogen aviation, how we want to address with a non-existent or a state, or with a state that we have here today, how we want to tackle that as to Mark Proto. And then we will say a few words on the basic DNA of a safe system, about some tools for risk mitigation and safety enhancement. And to conclude, we will say something about passive and active safety. And to sum it up, we will talk about the future outlook. As I've mentioned already, we would like to start with the key challenges of integration of hydrogen systems to the VTOL aircraft. This is especially the technological, systemic, and regulatory. So we can say with the technological ones that these are the specific properties of hydrogen, which we will mention later on, systematic or systemic. Here we have to deal with the specific properties of vertical takeoff and landing of aircraft. That means VTOL aircraft that work on a high security level. They have to be designed in terms of high security, in terms of vertical takeoff and landing. And then we will say a few words on the current legislative system, which is non-existent currently in our system. As I mentioned, I think we don't have to talk much about hydrogen, about its negative properties, because we have experts among us. But we want to use its positive properties, especially. We would like to address the challenges first, and this is of course, is his high flammability, and as we can't see that, and its diffusion, as it's very small, it gets into different materials, small materials easily, so it regarding metal, it diffuses, but it's also fragile. In other companies, I've seen they had to tackle with the challenge, and we saw some accidents as well. In terms of systematic challenges, I think we can see in these two pictures how our team is working as well. We have to consider also safety here. I don't want to say this is an unwanted parameter, but in these two pictures, you can see the hydrogen vessel with a tube form or shape and a spherical shape, and we have a compartment of different high energy areas which are separated by wall. We have batteries here. I will take a laser pointer. This space where the battery is stored should be separated from the hydrogen part. It can be solved by this way, or we could put another wall there. But regarding the biggest challenges, maybe this is the battery system, then the resistance, fire resistance, and then high pressure. The entire drive system works on a high pressure, high voltage, and cooling, thermal management of the entire system is also very important. And last but not least, this is the propulsion or drives. In terms of a vertical takeoff and landing, if they are switched off, then it's almost catastrophic. And this is why we have to deal with the challenges and design the device so that it's safe enough with high level of security and safety. I would like to skip or I would like to switch to legislative requirements and standards and what the current status looks like. The current legislation for hydrogen aircraft does not exist. Here we can see the extract of the timeline or the schedule that is defined by us in December 2024. It was presented back then, but I skipped that. But ASA is the European Agency for Safety of Aircraft. Through American legislation in 2023, the working group was created and they started to deal with the implementation or integration of the hydrogen engines into planes, into aircraft. I like how the synergy is developing, especially in this area. We can see other institutions here, also the British one. So British Aviation Authority, Canada and Brazil are other countries. So we can see a big group of big institutions preparing the legislation. In December 2024, this roadmap or this timeline was created, how they would like to proceed. We are currently somewhere here, so the challenge is really huge, which does not mean that the aircrafts with these small architectures can't fly or that they can't be performed. We will see that later. As we've said, big challenges for the organization is namely for the European, the administration as well, but it as a whole is to create a technological integration and basically to work with institutions to create or increase the preparedness and of the entire legislation. As the basic regulation for VTOL aircraft, the existing certification requirements could be taken through CS23, CS27, but in VTOL, for VTOL we have special conditions for VTOLs and special conditions for electrical or hybrid drives, but hydrogen drive is not included here. So this is the challenge, another challenge, how we want to do that. We should not forget, however, that safety is already included here since the beginning of the aviation, when there was no mention of VTOL at all. That means in the specific requirements you can see in a CS 23, 27, 2510, each system has to perform its function properly, and that means also that each system has to be safe, and no system can endanger another system in the aircraft so that it causes a negative response to the systems. These are basic principles since the very beginning of increasing the safety in aviation when VTOL were not produced at all. Now we will say a few words about how we want to bridge this regulation gap. This is namely through the usage of aviation standards on information reports, which are not yet included in the direct legislation, European standards, but they already exist. because they were published by renowned institutions as SAE, which is the Association of previously automobile engineers, but today it's also aviation engineers. But this guideline in terms of safety is also included here, and it deals with hydrogen cells. Then also usage of standards from other industries, for example, automotive industry. I've mentioned several of them in the presentation, but there are a number of them, but I didn't want to list all of them. This is just an example. Of course, we have some other tools for prediction and decreasing the risks, different analysis of the application that will be presented to you by my colleagues as well. These are different FAE analysis methods of final elements, simulation analysis of airflow, as well as, I will put it simply, you can design a system and create a system, prepare the architecture, and you will check the function of the system in further systems as MATLAB, Simulink, etc. Then we have different analytical tools and methods to decrease or evaluate risks as MATLAB, etc. We can see an overlap with other institutions here in VUT Brno, for example, from the Czech Republic. We can see an overlap, but also the verification, the validation on Earth, as well as checks on tests on Earth. So these are basic tools through which we prove the safety. How do we want to do that when we don't have a regulation? First, it will be the experimental aircraft, but the procedure is until the experimental aircraft is flying. First, we have to test its in individual components, then drives, so the parts as a whole, and then the device as an autonomous device, as an iron bird that has been mentioned, so flying testing machine that will be bound to Earth, and so it will fly to a certain height. We will verify the functioning systems in a real environment there. And then we will get to the experimental flying phase, or 2018 or 1139. The DNA of a safe system is simply that we have to define at the beginning the safety principles. In terms of VTOL, we are at the peak. So the safety level here is level A. That means it also depends on in which category the VTOL itself is, because VTOL aircraft are divided into two categories: the aircraft that fly above the populated areas, and then the other category. The first one is enhanced, the second one is basic, and this category flies outside the populated areas. That means at a lower safety level. I will explain that later. We can't hear the speaker. We can't hear the speaker. The mic is switched off.
So when there is a failure of any of the systems, it has to be able to reach the closest airport or a vertical point. But in the basic category, in case of a failure, the system has to be able to land safely. This also applies to certain drones, For example, if the battery goes out, they are slowly decelerating and landing. So the basic tools for risk mitigation and safety enhancement are the following. These are basically the basic milestones of safe flights. This is the leak detection, increase of safety in terms of fail-safe and fail operational design. It has to be carried out by safety factors and also the isolation of systems. And these systems have to be segregated or isolated, and the highest level is redundancy. But I would like to speak more about the redundancy because it's actually increasing of the safety systems. For example, you have fuel cells. If you create one 300 kilowatt or two 150 kilowatt, so it's every time better to have it separated. But again, it will be heavier, and these are the analyses we need to deal with. For example, this also has to do with drone engines. They have, in majority times, 3 cables. And VTOL engines, when we have double redundancy, actually it means it has to have a double coiling, and it means higher weight. When it comes to the safety margin or increase of the safety factor, for example, if we take a look at the hydrogen tanks, the high pressure there is of all the way to 700 bar, it creates many conceptual options of the tank itself. So there is really huge pressure which the tank needs to cope with. And now I would like to continue with the summary, and I would like to be speaking about the active safety systems. And these are basically systems which deal with the detection, but I would like to let the colleagues speak about it. We'll be speaking about the use of various sensors, and creation of redundant management. Basically, this has to do with the doubling of the systems, but also we need to take into account the software. There are 3 times, sometimes even 4 times backups. And basically, these are all challenges which we need to face. And of course, we also need to deal with advanced avionics and other advanced systems. When it comes to the passive safety, passive safety basically is the alleviation of the effects. And the structure should be designed in a way that it would be impact free. Last but not least, here you can see the picture are the ballistic recovery parachute systems. And at these airplanes, these systems are really developed well, and they're able to deploy the parachute and are really very efficient at low altitudes. Here, I would like to point out that one of our colleagues already has patents for such security systems, and actually collaborates with other companies which develop these systems. As a conclusion, I would like to say
that the highest priority for us when it comes to the challenges I have been speaking about when it comes to the installation of hydrogen power is the preparation of the airspace legislation, and therefore we will have to collaborate with the transportation office and to define the parameters which we want, and at the same time the authority will supervise the development of the prototype. So we don't want to yet certify the project, but we want to be showing the airplane as a whole and the upcoming development when it comes to the development of more advanced materials and more efficient methods are also a part thereof. So as a conclusion, I would like to say that safety is expensive because we have to increase the weight. When we want to increase the weight, we need to analyze and search for the ways how to decrease the weight. And also redundancy is expensive. However, it is something else that is something more than a human life. I would like to thank you very much. I know that this topic is not very attractive, yet it's very important. From my own experience, there is a comparison between the sales of cars and sales of interior. Everybody takes a look at the car, at the design of the airplane or a car, but then at the at last they ask, are you certified? Because the certification is the highest instance of security and safety. Thank you very much for your attention. I would like to thank the European Union and also the Ministry of Economy, who has been collaborating with us at the highest level. Thank you very much. Thank you. Let's move to the former design methods of non-conventional airplanes. We will listen to the presentation. Good morning. I apologize. I will not be speaking about the hydrogen in this presentation. I will rather be speaking about the ways or about the procedures during the development of a new airplane in general. My wife would say that we are only sitting by computers, nothing is happening, we don't do anything, but that is not completely true, because what is happening here is that at the very beginning are happening the most important things. Just briefly, I would like to show you a simplified overview. It's not complete. So this is an overview what we have to take into account during the development of an airplane. Basically, we go across many scientific disciplines. Mainly, we need to deal with the flight mechanics, whether the airplane fulfills the mission, what would be the costs, whether it's economic or not, and also the handling qualities, whether it will be easy and safe to fly. Also, we need to take into account the structural analysis. My colleague will elaborate later on. We will be speaking about the increased loads or insufficient stiffness. Last but not least, we'll be speaking about the certification, where we have to prove that all the prototypes are in line with our calculations. As I have already said, here we are at the very beginning where we have nothing in our hands. We only have many ideas and visions, and we have lots of time to think about it and to click in our computers. But in the course of time, the opportunities are narrower, and then at one point of time, the physical prototype starts to be produced, and obviously these opportunities are coming to a narrow neck. Here on this chart, when it comes to the costs, you can see that the costs are increasing. Of course, the price is not growing exponentially. This is why we cannot afford to make a mistake at the very beginning. This is really an extremely important phase for us. And basically, if I said something very simple, the quality of the output product is based and is depending on the quality of the methods we use. So today I would like you to get to know the most modern methods, and the problems we have been dealing with is the problem of the motion of the airplane in space. Those of you who drive cars, you know there are three kinds of freedom. We can drive to the front, to the back, or to the left. And when you are in a skid, you can also see a rotation. But when the airplane flies, the airplane can be moving also in other axes. Also, it can rotate around the axis. The mathematical solving of this differential equation can be seen here when the time change of the time vector depends on the non-linear equation is based on the outputs of the control system. Here you can see the numerical solution, and there is this three rotations, linear and angle moves. Here you can see the time change of speed from our high schools. You can see the formula which is called acceleration. This is really of essence for us because already during the design we need to set out the acceleration limits. For example, you can see the axis of speed, and here you can see the limits of acceleration, longitudinal when it comes to the z-axis. So if these limits were not set, basically we would have the problem with the weight, as already mentioned by our colleague, and the problem would be so severe that the airplane wouldn't be able to fly. So after we already know how does the differential equation looks like for our motion on the ground, if we take the example of a car into account, in inertial reference frame, there will be the Newton's law, where the force is depending on the acceleration and weight. And analogically, for the angle motion as well. So it's a little bit more complicated for the airplane. We're using inertial equations, as you can see on the slide. I would like to recommend the Flight Simulation and Control book about the differentials. But what we deal with is to state the aerodynamic aerial forces. This is the classical method, which took the model of the plane into aerodynamics tunnel, and we were measuring the forces and dependencies and using a very simple equation, area by aerodynamical pressure, and we can basically state the forces and moments. just to show you, here you can see 3 examples, and for the development of an airplane you have 300 up to 1,000 of such dependencies. And it is a problem for us because we are lacking time, and there is already many existing airplanes, and the development wouldn't be able to be paid for. So we need to search for better methods. From the 70s of the 20th century, we started to use the methods where we combine the aerodynamic tool with the equations. And the good thing about it is that we don't have to deal with thousands of dependencies, but we're able to deal with it in one software, and we only need geometry as input data. From the 70s, there is also this transient and aerodynamic solver, and we are taking a look at the middle area of the wings. This is high school mathematics, and we had a student of a high school who was able to program this method on a PC. If you are a fan of the Python programming language, on this link you can download this given implementation, including the example I have just shown you. So basically we divide the area of the airplane into 200 panels, and the disadvantage is that the fidelity is quite low. On the other hand, the computational costs is so high that for this example we are able to do this on 60 computations per second, which basically allows us to have this calculation in real time, because our computer games, the computer simulators, let's call it professionally, are using exactly this method when the computation can be done in real time. A more advanced method is a 3D panel method, where we model the area of the airplane using the including the flaps. This is more advanced calculation, and the calculation takes minutes up to hours, depending on the complexity of the geometry. In general, we use 20,000 panels. Here in the corner, you can see the limits of the particular panels. Novelty, let's call it, of the last decade is a 3D panel method with particle wakes. From the Milan Polytechnical School, you can download the program, which is called Dust. It was developed in collaboration with Airbus for their needs. And the main advantage compared to the panel method is that here we use particles instead of flat panels, and we are able to deal with the interference with other objects. The usual panel methods are facing difficulties when doing so, and here on this picture you can see a propeller, and this calculation took around 1.5 hours on a workstation. Had we used the current methods, for example, the final volumes method, it would take a week. So there is a huge time saving, yet having a very good quality. Here you can see a mistake in the headline. So this is the final volumes method. Sometimes it's called computational fluid dynamics, and it's based on the modeling of the air around the object, and the volumetric items are being used. and it also has to do with relevant equations. We need around 5 million to 100 million elements, and also we need a very quality hardware where the computational times are sometimes even months. If you want to take a look at it, the website is openfoam.com. Anybody can download it and start dealing with it. Big advantage of this model is that we can also deal with large details. For example, in this given example, you can see the flow close to the wind, also including the modeling of the gap. We can also deal with the heat transposition. The disadvantage is that we need really very high quality distinguishing of geometry. We dealt with this with Mr. Gajdos, because if you want to develop the airplane, it doesn't only need to be able to carry out the mission, but you also need to take into account the design point of view. Colleague Gajdos is a designer, therefore we have used open source Blender, and my colleague is able to design the airplane in such a way that it fulfills its aerodynamic role, yet it's good looking. So we had to give him all the aerodynamic areas. If you're interested in this, Mr. Gajdos will give you more detailed information. So this is about it when it comes to the methods. And what is the analysis result? For example, we have the velocities, accelerations, pressures. We also deals with the pressure distribution, inertia forces, and we are also to take a look at the loads due propellers, but nobody is actually interested much in this. What is interesting is, when it comes to the authorities, is the distribution of the effects. So we need an automated process which, based on the plethora of information we can see here, get to the largest arrows. Here you can see the presentation is wrong because there is an equation missing. Here on the download thing, you can take a look at the library. I'm one of the authors thereof. And if we use the methods of final volumes, we have, for example, 100 million elements. And in the domain, at the surface of the airplane, we have, for example, 4 to 20 millions of elements. And in case of loads, there are thousands. And if you multiply this for every single elements, we have billions of various combinations, which is basically useless, and we need to reduce this data. So what we do is that we carry out a cut through our model. We count for all the given elements, for example, 40 million or 50 million, we count the final load and we add them all together, and basically it creates the power of load on the element, and therefore we are able to use this reduced information for strength analysis and for the design of the airplane itself. So this is everything from my side. Let me reiterate that the quality of our final product depends on the methods we use. Thank you very much for your attention.
Ďakujeme veľmi pekne.
Thank you very much. I think we've heard a lot of interesting information. We have some space for discussion. The first question was received in Slido, and it's directed to Mr. Takac. As you've said, the aviation regulations for hydrogen aircraft do not exist. In what way will the certification procedure start? Mr. Uhrik. Thank you for the floor. As the regulations do not exist, as Marian has said, we would like to use the project to create or to be co-creators of the legislation, and we want to produce that aircraft with the transport industry, and the representatives of this association are also here. So this is the way how we want to solve it. So this will move the importance of the project forward. Mr. Sinai, yes, just a small fact. We've collected some norms for hydrogen technology, namely 936 pieces, different B norms, American norms, different standards. Within expert group, we've done that. We've defined 43 binding regulations for hydrogen. This is not targeted, however, for our conditions. I would like to invite you to get our hands, to put our heads together to use the authority for measure analysis as well, and also Transport Authority, the Ministry of Transport as well. That would just widen our portfolio, and we would include the Ministry of Transport. We can give an assignment to the ministry. It's a hard job, however, but let's try it from this point of view, because the same will be faced in terms of trains, cars. This will go through the Ministry of Interior. This will go through the Ministry of Transport. Thus, so we should stay in touch, and we should communicate with them. Tell them, gentlemen, please do not sit just in the ministry building, but search for this hydrogen technology stuff. Who would be able to join us, because we have to approach the Ministry of Transport and together create cooperating synergic group. We shouldn't proceed through different channels for different hydrogen purposes. Thank you very much. Maybe we would have some space for one question. However, if there is no question now, thank you for your attention in this panel, and let me invite you to the brief, short break, some refreshment, and one more organizational remark, as one of the presentation of the following block will be in English. If someone of you would like to listen to the interpretation, you can collect the headsets at the entrance to this hall, and other presentations will be in Slovak. So we will meet here in 15 minutes, 10 to 11. So please be here back on time, so that we can start on time and enjoy your break. Ladies and gentlemen, let me invite you to the second block of presentations and subsequent discussion. I would like to mention once again within this block, one of the presentations will be in English. So if it helps you with some the professional topics that you listen to the interpretation at the entrance to the hall, please get your headset. As I've already announced, it will be just more and more complicated in terms of technology. The next topic will deal with the design of parameters of aircrafts, and I will pass the floor to Mr. Melish. Good morning. I'm Michal Mališ. In the team, I have the role of senior in terms of design of the aircraft. It won't be more complicated because the colleague has held his speech, so now you can relax and look at the nice pictures. My presentation, or the design of the aircraft, we will deal with that in a whole with all parts, with the chassis as well. I would like to mention the design of primary supporting airframe structure, stress analysis, definition of requirements for manufacturing, what our group deals with, and definition of structural tests, and of course certification. This presentation will be also about the presentation of the team. Because I think Tomark has managed to collect from our Czechoslovak region quite a nice group of design constructors, which is at the Central European level quite unique. I would like to mention the projects on the one hand, with which we've dealt, individual partners of the team or members of the team, and then the individual assignments that arose out of my presentations. We had smaller and bigger aircraft, from the transport aircraft up to the commercial, also prototype aircraft, but also with art. Here on the bottom part, you can see the installation of David Czerny in Prague. The installation is in Prague. This is a butterfly that reaches across 4 floors, and you can see the implementation of the procedures we've learned with the design of aircraft. So my presentation will have a popular form. Do not be afraid of any equations. One of important parts is the design of the structure. In terms of software, we use CATIA system in aviation. It's a standard, also a maximum we can pay, or we can afford the design in detail. It's important that software has a direct connection to the manufacturing. It wasn't the standard 20 years ago. Now it's a standard for the production of such elements. So we almost do not need any drawings. It's a usage of software, therefore we need a skill. Medium experience usage of user of CATIA. So what I need 1 week for, they would need just 1 day. Not because they have faster fingers, but it's a special knowledge which is bought from them by foreign automotive industries. So this is one of the special properties of this team. This is the current status of the development. We are in the stage of preliminary design, where we play with individual aggregates and we try to place them within some limitations into the structures of planes, aircraft, to ideally to determine the center of gravity. This is the focus of the slide. This is user friendly by moving individual components representing individual aggregates. We can compute the center of gravity, which is important for us to design the aircraft that is able to fly. This stretches over all parameters. It took several days in the past. Now it takes just several minutes, which shortens our time significantly. In the original design, it's important to propose as many design versions as possible. Pavel Schoss has already talked about this. This is the load calculation of the aircraft wing. This is an elite discipline of the aviation designer. Pavel hasn't mentioned, because he's very modest, his system that he presented within his lecture or presentation. Fire Vodochody were interested in this design, and they use it for a light battle aircraft in Prague. I think it's a software at the level of Central European significance that is available to us. The dimension, designing the structure, is a separate chapter. We have to be aware of the fact that we design structures, not that we check we check its strength. We compute the loads, then multiply it by 1.5, which is the safety. The first one is operational. One multiplied by 1.5 is the computational part, and we design the part of the structure. This is just general thing, and we want that the structure can bear 1.5 operational load, and after several seconds it can break. So we do not design the structure to hold, to break, but after 150% of the load, because only this way we can reach our purpose. This is namely firm structure is the basics for everything that is flying, and thus we will have even a much more emphasis. So we have to focus on the weight of the structure more here than in a standard aircraft. Every gram is good that we save. Designing the structures in terms of software is based on several algorithms stretching from simple Excel computations at the level of middle school computation through to more complicated, up to the standard software method that is complete standard. This is a global wing model on which we will perform the proposal of the composite structure, and each console will be checked individually. What has been seen recently, algorithms of optimization, which is algorithmical optimization, where this model on the top part So we let software to take those parts of the structures that do not hold anything, that do not bear any loads, and thus we get a generic, such a generic shape by which we can achieve the lightest structure possible. So these are again algorithms that are implemented and can help us. Nevertheless, the most important knowledge is the knowledge of the technician. If we let AI do that, the person in the background is always the most important person. A specific feature is also brought by a composite element. If we take a sheet metal, which was a standard material for the production of aircraft in the past, we can buy the sheet metal in the shop, which is produced somewhere in the works, and is of a standard quality. We do not have to take care of the quality of the sheet metal or sheet plates, but with the composite materials. So it matters how it's produced. The thinking is different when compared to using standard materials. Composite is a standard material, but the philosophy behind is different. So disciplines like quality of materials, technology, and the computation and different can't be separated. They have to be dealt with globally. It's demonstrated here by this picture, building block approach, which says that the level of description and knowledge of the quality of material versus data for firmness computation, we have to describe the material as well as the mathematical model, and we have the first floor of the pyramid up to the panels, which is the third one, and then it's a check of the entire wing or body of the aircraft. We have just one a piece of that in each of these levels. The material brings some new specifics which we have to be familiar with, and they have to be included in the computation. In another slide, you can see the qualification of one material at the bottom level of the pyramid. Building approach, pyramid. Let's have a look at one reinforcement, so that it's described as we need it in the design. We have to perform 80 specimens, 20 for four different types of tests to describe all material constants needed for the computation. We have standards for that, and it's no science, no rocket science, but it costs quite a lot of money, which we need to spend at the very beginning of the project, because as we are able to produce can be shown in how we calculate that. So before we do the first drawing, we have to know the materials behind each figure. There is a story behind. If we don't have the test at the very beginning, at least we need to have the experience, and everyone of the team has some experience, so we are, I think, quite well prepared. We have also the analysis by method of finite elements. Our structures will be sandwich type. This is shown in this picture. Between two thin coating layers, dozens millimeters, there is several millimeter foam that could be 3.5-7 millimeters. This is extremely light and a strong material, but it's difficult to analyze, to evaluate. Why? So critical load of the material in terms of firmness is not determined by the firmness of individual layers, but by their combination, by this construction where individual proportions between the strength and solidity determine whether the sandwich structure will collapse with a certain load or not. Here it's shown by this individual crash examples, and something like that can't be computed by using commercially available softwares in the market. In other words, so there are commercial softwares which allow us, this is more expensive, but standard softwares do not provide that. Otherwise, we are not able to compute it. This shows how it's the result from the finite volume, finite element method. A composite post-processor, this is a filter that we designed in our team. This is able, based on the finite element method, compute all these results that we are able to determine whether we can face the sandwich failure or not, and then we depict this picture. And without that, we are not able to move forward. It's possible, but it's very complicated. The results are not good if we do not use similar software like that. So software like this are commercially available, but they are very expensive. Another chapter, we will deal with intensely the definition of static loads. So, a wing in static testing. This is the situation where it should break after this, after 150% load. This is not shown properly because it's not shown properly. I wouldn't take pilots to such tests because they could be afraid of flying with these aircrafts if they see how it breaks. But it's part of our life. It's adrenaline because if wings fly in the air, they break without warning, and they fly in the air. So it's quite adventurous if you see that, and that will be also part of our job. We are able to cope with a number of things, but with some things we will need some assistance. So this shows that we can cooperate with universities, scientific institutions, definitely in aeroelastic phenomenon with this special aeroelastic engines, with passive safety. Well, we could deal with that, but it's a demanding job, but it's interesting in terms of research. So we would like to cooperate with partnership institutions. So we would like to also analyze the fatigue of the materials. That's all from my side. I would like to thank you for the attention. I would like to wish Slovakia that the project is successful. And I would like to thank the Slovak Republic and its representatives that they support us in our job, because in the background of the project, only here, the relationships between individual institutions can be created so that we perform such projects, and I will be happy if I can take part in those projects. Thank you for the attention.
Thank you very much. It was really interesting to hear that besides CERN project, the internet emerged, so maybe there will be other projects that will emerge.
Ritter to the stage, and That's also a reason why I speak English. And he will talk about the design, manufacturing and certification of the hydrogen tanks for VTOL aircraft. Mr. Vittorio, the floor is yours.
Thank you for this introduction. So it seems that somebody is speaking in a foreign language for the first time. I don't know if there's somebody else, but at least I will try my best. I am from Germany, so it's also not my mother tongue, my mother language, but I'm used to present in this language. And some words to me. It was just 40 years ago that I started working, and I still did not stop, and I'm not planning to stop. But it was interesting, this point, because I was starting with a job. One of my first jobs was to produce or to design pressure cylinders, high pressure cylinders. They were from steel, heavy, very heavy. The same company I worked for was a market leader to produce filament winding machines. Filament winding machines are essential to produce lightweight cylinders. So the combination of the two was a good coincidence for me to become an expert for lightweight pressure cylinders. Now, I am a little bit desperate here. I don't know how to start my presentation. Please. Okay.
And you can continue with that machine. Is it working? It is working.
Yeah, this works. Okay. Good. Okay. So let's start. I will give you an overview about some history applications, geometric shapings, particular design, serial production, and an outlook about lightweight pressure vessels for our application here. First of all, what is very interesting, in the universe, 75% of the mass is hydrogen. On Earth, we find about 0%. So why is this the case? Well, it's a very simple example for explanation. Everybody likes the sun and the sunshine and the warming of the sun. The sun is nearly 100% hydrogen. But nobody wants to live there, nobody can live there. So that means we have to generate hydrogen if we want to use it as an environmentally friendly fuel, and this is the motivation for us. So the good reasons to use hydrogen lead us to the point that we have to produce hydrogen. And must be a pointer here, maybe. This is not a good pointer. And if we differentiate these hydrogen storage, we have different possibilities. One possibility is that we just compress hydrogen because we need to compress hydrogen. It has a very high volume. If we don't compress it, a compression method is, for instance, something what increases also the value of the hydrogen, means also the production price. So if we liquefy hydrogen, it will cost 130% compared to compressed hydrogen, which I put at 100%. That means, sorry, this is a little bit wrong here. The liquefaction process is 130%, and the 140% must be at solid state. So that means that it is important, if we use hydrogen, that we have to pay the price for the production and probably something else, but it is essential to understand that the price levels later will lead our customers to the way how we use hydrogen, how we store hydrogen. So, of course, we come from fuels, gasoline, whatever, and just a practical example. If we want to drive 100 kilometers with our passenger car, we use this volume, which is equivalent to 6 kilograms of gasoline, for instance. If we want to store 1 kilogram of hydrogen at 1 bar pressure, we need about this size of cylinder. 1 kilogram is also a quantity where you can drive a distance of 100 kilometers. If we now just compress hydrogen to 350 bar, there are different volumes on the market, 350, 500, 700 bar. If we use 350 bar, we have about this volume to store. And if we compare the liquid gasoline today to the volume of tanks which we need for hydrogen of 350 bar, that means such a tank is 8 times bigger compared to what we are using today. A small look into the applications of hydrogen as an energy carrier. So speaking about a cylinder or a vessel containing high pressure hydrogen, I compare this with a battery. So it is just a medium to store energy, nothing else, but the technology is different. Let us show, I don't know if this will work. Let us show at, we have a video which does not start now because we have 2 screens. Let me try to fix that. Okay, it seems that I have a problem here. You did not integrate the video? Okay, can you somehow? Okay. Okay, I'm sorry, but the video was not integrated here. So the video shows the market leaders' introduction, and it is about applications which are mainly on road. So after the video, I wanted to ask you if you miss any applications, and I would like you to say, yes, we are missing flying applications, of course, because we have in the applications very clearly dedicated road and ocean transport. What you see on the first row, so this is trains, we have ferry boats. We don't have applications anymore, which we thought at the beginning, okay, when can I buy my first hydrogen car? This did not work because battery is quite correct technology for this one. We have other applications which do not work. If you want to cross Atlantic, Pacific or something like that with an aircraft, you would need so many space for your compressed hydrogen that only the pilots could be carried on this aircraft. Also, if you use liquefied hydrogen, you would use about 1/3 of the fuselage. So that means you would leave a lot of customers on ground, and this is not the right application. But for shorter distance, it is the right application because batteries at a certain point don't work, and it would be good if somebody could bring me back here into the presentation. I'm a little bit lost. Please help me. Okay, looks good. Thank you. Thank you very much. So we are now focusing on these two applications on the upper right side. And of course, VTOL is what we are looking, but also aircraft transport for shorter distance within Europe is the correct application for hydrogen. Batteries don't work, and hydrogen would be the right application. Why do I always compare with batteries? I compare with batteries because the usage of energy by electricity in batteries is cheaper compared with hydrogen in the production. And it will always be. To produce hydrogen is more expensive than to just store and recover electricity in a battery. So, with other words, there must be a reason to use hydrogen. So the production of hydrogen today, of course, must be green. There are other production of hydrogens which we use in the industry, a lot of hydrogen which is produced, but it is not environmental friendly. So the future is green, and on this side we have the different applications, and looking at the circular usage of hydrogen in a VTOL, we have the production, we have the usage in a storage tank, we need a fuel cell, of course, a lot of systems to be integrated, and I am very happy that the colleagues take care of so many other parts apart from the storage of hydrogen, because I don't know anything about how to design an aircraft or VTOL, but I know how to design these storage systems. And finally, in a circular usage, the outcome will be water, and this is accomplished to save our future planet. And this is the only part which I will be focusing on in the aircraft. Of course, it is also necessary to build an infrastructure, and we need to store hydrogen. We need to charge hydrogen into the aircraft, into the VTOLs, and there's a lot to develop in this direction. Well, there is an important question. Why do we develop a unit which is already existing? You can buy a lightweight storage tank for hydrogen. It is on the market. The answer is the existing ones which are on the market are focused on road usage. We need to make this suitable for the usage in VTOL. So this picture may demonstrate you differences which are easy to understand. It is always the spherical shape which is the optimized shape to maintain high pressure gases or whatever. A cylindrical shape is easier to integrate in vehicles and aircrafts, but the spherical shape is lighter and has a better usage of the strength, of the resistance of the materials. This is why we started again to improve and to develop pressure cylinders for our use. As I told you, 40 years ago, I started my career, and after many, many years working for market leaders, I organized my own company, and I'm an expert to design plants for the production of such cylinders. For instance, what you see here is a plant to produce 30,000 cylinders per year, and this contains all the technologies which are available to produce in liner, for instance, to do the filament winding, to do the testing of each cylinder. We have storage devices, and at least one of 200 cylinders also needs to pass special tests like burst pressure test and cycle tests, so that we can bring the produced cylinders to the market. So this is this occupies a space of about 5,000 square meters. So it's about 100 by 50 meters. And this is what we need finally for the scale up to really produce high quantities of cylinders. Now we spoke about regulation, about norms, about standards, which are not completely available for our applications. But most of the standards to make sure that the cylinders resist the loads, they have a lot of approval tests, which I listed here. We have 39 different tests making sure that the design of the cylinder is correct. Of course, we simulate the design, we do FEA analysis and everything, but we must be sure that all these tests are passed and there is no compromise. There is 100% quality which must be supplied to the market. No failures, zero failure strategies, please. Now going to the regulation, we already saw some numbers before presented. I show you some more numbers like ISO 11111-3 and so on and so on and so on. There's also a Chinese standard, this one. But what is interesting on this chart is that the safety factors, for instance, for a burst pressure are between 2.0 and 3. So you can probably see 2.0, but it is times the test pressure. Test pressure is 1.5. So in total, we have a factor of 3. So that means these experts who come together and who define the standards obviously are uncertain which is the right level of safety which we have to produce. And this safety is, again, this is for transport. These are special standards for transport. It is not for fuel on board. So there are much more standards than these. And I would be happy to have standards as a guidance where we can say, we follow this standard, aviation standard, and I'm very happy to hear the words that you have the plan to go this way. This is the right way, so that we have a focus on this one. Okay, my last slide about barriers. I supplied more than 200 applications to aerospace systems and aerospace companies. So I remember one time an engineer told me, before a rocket flies, certifications which fill in the inside of the rocket must be produced. That means a rocket cannot start before the paper is produced to fill the rocket equivalent of the inside of the rocket. And this is also a situation which we are probably approaching. We have experts and we have the technology, we have the softwares, everything to tackle the technological barriers. And we started already. But regulatory hurdles must also be tackled, and in parallel, we also must use administration efforts to come to this point as well. We cannot bring our important technology on the air without the approval of the regulatory and of the politicians. So let's take them together with us, and thank you for listening.
Ďakujeme veľmi pekne.
Thank you very much.
Teraz opäť prejdeme do slovenského
Let's
jazyka
switch back to
a
Slovak.
ďalšou témou bude
And our next topic will be artificial intelligence and flight management services. Mr. Malish already said that it will be simple with beautiful pictures. It will not be. But Mr. Kudlachak will explain it to us. Feel free, the floor is yours.
I'm František Kudlachak, and I'm a member of the team for development of electronics and development of the program and everything that is related to electronical part in the aircraft and as well as programming. This is part task of our team. Now, our general architecture of the aircraft in terms of electronics, I would like to deal with a specific drivetrain. That means the drive system. Then I would like to mention the AI application in the development of the aircraft, also during the operation and flight of the aircraft. And then I would like to conclude with the further plans and how we can improve the entire system. The system architecture is quite complicated, comprehensive. It can be divided into two basic blocks. One is a high voltage block dealing with a nominal voltage of 800 volts and a low voltage that has just lower voltage, and then another voltage that is a part even under the low voltage part. So in standard procedures, we have aviate, navigate, and communicate. This procedure is applied when designing the system. That means aviate function, the flying itself. It's managed by the central computer to which different sensors are connected. This control computer is the critical part of the management. 3 times a backup, also the entire systems that contribute to the management of the aircraft. Those are 3 times backed up. The second part is navigate. As the entire aircraft should fly as a drone. So this is also quite important. The centers for navigations, cameras, radars, or special GPS, all those elements are in certain cases made redundant, like GPS. The last part is the communication part. Communication between the ground level and aircraft is ensured through that, also between the aircraft and the tower. This communication is divided into several data lines. As those provide different speed transmission of multimedia data. Here we have a broadband for communication, for management and telemetry. We have another backup band. This data is connected into ground station, which has backed up connection, and from this station, the operator pilot can navigate and control the aircraft. I would like to mention that within the low voltage system, we have a backup battery. So if a high voltage battery fails, the aircraft can work in terms of basic management, steering, and we can use we can use the parachute which as well. We work with performance, and the main part of the hydrogen system is a hydrogen cell, which should have a 300 kilowatt basic performance, and we are able to distribute this performance further. In that, as we need 800 kilowatt for vertical Lindov, we have high voltage battery. We have 305 kilowatt hour. It's not big, but together with that, we need to provide 600 kilowatt power. So it is small, but it has to be very efficient. An important part is a distribution, a high voltage box in which we have safety circles. If the voltage goes to the main body, to the skeleton, the other parts can be switched off. For high voltage distribution box, we have drive. The drive of the aircraft is ensured by 8 engines with 800 kilowatt performance, which are activated during the flight, and until the horizon flight, we activate 2 other engines with the performance 250 kilowatt. So during a horizontal flight, we have a surplus of energy. So like 50 kilowatt can be used for charging the battery, so that during landing it is fully charged. In case of failure, the aircraft has to be able to land safely, so we have to design it with a certain safety limit. When developing the entire engine system, the main parameter is the weight. Several of these technologies are on the limit, which can be achieved with available technology. So in certain elements, we will design our own proposals. When designing the entire system, during the entire system, we've been assisted by the AI, and this is integrated in the project in certain phases. Also in the preparation status, it allows us iterations, mechanical, electric ones, when determining the finite element method, mesh, and with the regulators, AI can help us. And of course, with documentation as well. AI does not help us just when designing, but also when flying with the aircraft. Its broad usage in advanced machines can be also by us. To have an idea about that, the aircraft will behave as an autonomous drone. For its steering, we use different methods. These methods and these sensor fusion, autonomous flight functions. Important part are advanced predictive models for maintenance of the machine, and increasing the efficiency when planning the routes, or when charging is necessary for long routes. During the flight and takeoff, we need to create a 3D environment around the drone or aircraft, where we put together all sensors. We will use LiDAR sensors, satellite systems, inertial units, or navigation, and all this data has to be accumulated into one model, so that we can see within in the area we can identify the barriers, plan the routes, and adapt to possible dangers. The entire virtual world created in the aircraft will be augmented, namely the outputs from the exterior systems like weather forecasts, forbidden spaces, or current communication from for example, tower. When using the aircraft, we will have 3 modes. The first one is takeoff. As its VTOL system, the takeoff will be vertical. Before each flight, the system can sense the system environment and identify the start vector, which can change during the flight, as the vertical takeoff allows quite fast reaction to changes, and after roughly 50 seconds, it switches to transformation to the horizontal flight. We add the additional engine, and during this horizontal flight, during takeoff, we have 800 kilowatt, during horizontal 250 kilowatt, and during this cruise, the aircraft evaluates the environment. If it's a city area, we have protection against crash, monitoring of planes, aircrafts, and when we get a message from the tower, the system can automatically replan the route. In the last part of the flight, we have landing. It's possible to program the system so that it can land in any field. So the sensors of the aircraft evaluate the suitability of the environment for landings. It has its cameras, sensors, and it can determine the landing vectors for heliports. It's no problem, but for non-standard areas, we have AI that is able to evaluate the suitability of the landing space. Here we also switch on the vertical engine, and the system is switched off safely. The second important part of AI is predictive analysis and detection of some imbalances in the system, in terms that we determine most parameters in the aircraft and evaluate the changes in behavior. This analysis allows us to detect the issues, either fatigue parameters or fatigue parameters of electrical components, cables, either cables or increase in temperature. Of course, we have quite simple systems that can allow us to do that through some threshold parameters, but AI can search for slight changes in patterns that occur in the system and can make us aware of what to look at. This will allow us in the future to decrease unplanned failures of the entire system and can bring the saving in maintenance as well. The fourth big part of usage of AI in this aircraft is planning the route. For standard flights between two airports, it's not a big advantage, but when we want to land in an urban area, for example, this possibility allows us computing the routes based on efficiency and terms of decreased consumption or higher speed, or planning the routes based on charging stations. what is done by e-vehicles, that can be done in the air, so decrease the flight time and, of course, improve improve a planning process. We can imagine the mission or the flight as such in this way. After starting the entire system, it senses the environment, downloads the weather forecast, flight conditions, and determines the flight and computes the vector and starts during the cruise. It gets information from the tower through different systems and also information about charging stations, maybe in the future, and computes subsequently its route during the cruise. Takeoff and landing as well. We have avoidance systems, avoiding barriers, and in each of them the system is a bit different. During takeoff it behaves differently, this system, and also during landing in a different way. During the entire operation we monitor the functions of the aircraft. During a landing we have a system that visually plans the vector, landing vector after the cruise. After landing, the data is sent to the ground station, or it is sent to a joint server where it can be evaluated and we can improve the regulations for the engines or planning of the route. Why this all is done? Why is AI implemented in the entire solution? In the first case, this is the safety that matters in aviation, either through detection of barriers or anomalies in the system during the lifetime. Increasing the efficiency of the transport is the next one, thus decreasing the costs and expenditures. As it's a hydrogen system, it's naturally greener transport, and the objective is to make this transport available to the majority of people. And the possibilities that allow all this to us is continuous improvement of the system. After the cruise, based on the data, we can improve a flight or steering management data. What is ahead of us in the future? I mean, after beyond 2030. This is the possible integration of the entire system into a connected flight. The aircrafts or drones would communicate between themselves, and they could exchange information about weather, about the status of the environment, but also steering information regarding the individual systems. The second part, as it's been mentioned, is the integration of the aircraft into smart city infrastructure or into the infrastructure of hydrogen systems, where planning transport would be quite autonomous. This is the future that we can see ahead of us. I hope we will get there. Thank you for the attention.
Thank you very much. The next topics will be the conceptual designs of VTOL airplanes. So we'll be speaking about the aesthetics and performance, and the upcoming presentations. We'll have a duo of presenters, Mr. Orsak and Mr. Seman. The floor is yours. This is my first experience with a microphone, so let's start. Okay, now you should be able to hear me better. I will mainly be speaking about airplanes, so everybody who's from this industry hopefully will appreciate my presentation, and I would like to tell you more where we stand with Tomark airplane. I will be speaking about the procedures which are already tested in order to help you to get to the objective. And the first phase is the so-called new concept idea. The conceptual phase is the first phase where you basically determine the basic concept of the airplane. So you set the ratio of wings to the body, and you basically make the basic parameters more precise. And at the same time, you have to ask yourself whether your concept is feasible from the production point of view and also from the point of view of operation. Such a iteration procedure gives you a concept that meets the basic layout requirements, which are input information of the project. There are more concepts which you need to use a tool for to decide on what the preliminary design phase will look like. So basically you already have the first more precise phase of the project. In the first phase, you take several concepts into account, and then you continue with the only one that you have already selected, which most likely is the best one, which has the potential to be the project that will be developed subsequently. So this is the first phase. There's also the technical requirement, which will be described by my colleague. As already mentioned by Matusz, I will not be taking a look at it from the technical point of view, but rather from the operational point of view. So we already have parameters which we need to define the tool itself. And for us, this parameter is the use of hydrogen as a sustainable fuel for humanity from the point of view of ecology. So are we going to be able to use hydrogen in a gas form, in a liquid form, and we will create energy using fuel cell? At the same time, for us is of key importance the vertical takeoff and landing, which is critical for use in cities where the infrastructure is limited. For example, there is no subway, no underground transportation, and we need to think about a very efficient mode of transportation, but we don't have enough room for runways. At the same time, we defined 4 people, which will be 2 passengers and 2 members of the crew. As Matusz already mentioned, we created several concepts, and in order to create one which will be meaningful and will have future, we cannot be only thinking about conjunctures, because it will be very subjective. Therefore, we took criteria which are objective. So we take into account aerodynamics, efficiency, range, maximum speed, and from the point of view of the operation and the investors, customers, or people who will be taking a look at this vehicle, we need to achieve a wow effect in order to be accepted. So people should get used to it somehow. People should be somehow attracted to such an airplane. At the same time, we should be thinking about the potential of a series production and sustainability. And from the development point of view, it was already mentioned here, we have various aspects which need to be maintained. For example, the implementation of the hydrogen drivetrain, which is still not normal one. Of course, this includes transfer between vertical and horizontal takeoff and landing. This shows us safety risks, which however are feasible, and we'll be able to get through it. Certification is also a part thereof. And last but not least, it's the operations. What we need is the airplane needs to be operational in any kind of environment. The maintenance has to be kept at low levels. The costs and time that the maintenance will need to be low. Also, we need to take into account that the airplane will be mainly used in city areas, and all these parameters allowed us to compare various concepts, and we therefore identified those which have a potential for future development. Certain projects are interesting, but are not as feasible as the others. We have already discussed from the very beginning, Mr. Uhrik said that the helicopter is not a new thing. It has been with us for over 100 years, but we would like to show you really interesting ones, which are of essence for us. As we know, every single airplane has to have a mission. For our vehicle, the vertical takeoff is important, after which there is a transition from the vertical takeoff to the horizontal flight. And in this moment, we need to secure the highest safety. When the vehicle is already in the optimum altitude and velocity, then we have the pending reserve based on the certification due to the fact that we have to anticipate something that is unable to be anticipated. For example, if there is any obstacle with landing, we have to be able to change our plans on site. And last but not the least, it's descending to hovering. So we have already said that we have more concepts, and we would like to show you how these could be used. For the shortest tracks, all the concepts are suitable, but the best could be which is now called the quadricopter, which looks like a helicopter or a drone, because it doesn't need any runway and is basically should be used for short tracks, has very good maneuverability, and for the longest flights, around 200 to 300 kilometers, those two concepts which already have certain loading areas, boarding areas. In order to be able to use these concepts in our environment, we have to keep in mind that we need to deliver silent operation, which will be described in more detail by my colleague Matusz. Just like my colleague already said, we have a whole scale of vertically taking off models. We took a look at a couple of those and developed certain that would be able to evaluate the production ability and operations ability. And I would like to show you 5+1 concepts which we consider as feasible. Out of these concepts, we select one which we elaborate in more detail. The first concept is the helicopter of one bearing and one balancing rotor, which basically deals with the elimination of the main moment that emerges at the main propeller. Here you can see the compound helicopter, which has one more wing, and the wing has a single use. During higher velocities, it creates power which could be also used to help the main rotor and get the surplus of performance, which allows us to accelerate or to move higher. Except for the main rotors, there are also other auxiliary engines which are only used for the horizontal flight if it helps the efficiency of the operation. The second concept is the compound helicopter type B with the so-called coaxial propellers. Such a helicopter doesn't need the balancing rear rotor, which is an advantage in saving the weight of the transmission system, which doesn't have to be in the back. And such a helicopter has more power, and also it has certain disadvantage, which is high center of gravity. However, its advantage is very good efficiency. So out of the proposed concepts, this one is energetically most efficient. And another type of such a helicopter is the so-called tandem helicopter, which uses two bearing rotors which are horizontally aligned, and it's quite a robust solution. We need to deal with the synchronization of the rotors, which nowadays doesn't create a large issue. However, it is very important. In this helicopter, there are quite high demands on the parts of the helicopter, mainly its body. Therefore, we decided to amend the project, and the main part will be the tank with the pressurized hydrogen. So the body will be the bearing construction. So it has certain advantages when it comes to the endurance abilities or the range of flight. And such a concept allows us to create large space or room in the body, and it's a quite nice solution from the point of view of the cabin for the passengers. Another concept is the quadrocopter, as I have already mentioned, which is similar to a drone. At this concept, we use 4 rotors which use the change of revolutions, which allow us to maneuver the helicopter in the space. It has very simple body, but we have certain troubles with certification if human passengers are supposed to be transferred, because the reliability could be a challenge. But it's a very compact solution for the shorter missions, as it was already mentioned. And here I would like to show you one special concept which we took a look at from the point of view of feasibility, and it's this so-called gyrocopter, or the whirlcopter, which uses the upwind in order to turn the front propeller. Its construction is quite simple, which accounts for savings in weight, but we wouldn't be able to vertically land and take off. This is why we have installed engines which turn the bearing rotor during the phase of vertical takeoff and landing. The disadvantage is the noise created by the propellers, because there are 20 to 30,000 revolutions per minute, which is really extreme from the point of view of operations of such a device. And the last concept I would like to show you, and I can tell you that we have decided with this concept to move on with this concept. This is the lift and cruise type. This is a classical airplane with a wing on which there are uplifting engines installed, which only work during the takeoff and landing. During the cruise phase, this engine, which is in the rear part of the body, these uplifting engines are in the standby mode and do not help the vehicle to fly during the cruise. There are many criteria how to compare these vehicles. We selected the so-called aerodynamic efficiency model, which is a good parameter to compare these motor crafts. Having a look at these curves, you can see the highest potential of the further engineering development and the challenge where we really could move forward this project. The lift and cruise on the right-hand side will have an objective to increase the range of velocities at which we would like to operate the craft. So we want to increase the efficient velocities. As you can see, the least efficient concept is the quadrocopter concept, where already in this first stage, it already achieved its limits. So there are not many opportunities to increase or improve its characteristics. So we will move on in our project with the lift and cruise airplane. So we have 8 lifting engines plus 1 cruising engine. So this is everything I wanted to say. As a conclusion, I would like to thank you and tell you that we efficiently found the best model, which would be the best way to move on. I would like to thank everyone who believes in us, and we also strongly believe that we will be able to deliver. Thank you very much. Thank you. I think when we speak about the vision of the already existing project, it starts to be interesting. And what also starts to be interesting is the future or the view to the future in the imagination of Tomark Proton. Such a concept and the vision of future. This will be the topic of Mr. Gajdos and Mr. Uhrik. Feel free, the floor is yours. Thank you very much.
I wish you a nice day. I'm Michal Gajdos. I'm Tomark Proton. I'm working as a designer. And it's a great honor for me to be here today and introduce to you our hydrogen ecosystem mobility as well as other visions of Tomark Proton. Our first presented version refers to the rescue of human life. How effectively we can deliver human blood organs or other materials for medical purposes. The answer is the network and infrastructure of smaller hydrogen-driven aircraft. The delivery is very fast, ecologically good. That means the corridors are not limited by nature protection zones and can fly for wide distances than electric devices. But the rescue of the human lives is not just in the hands of doctors, but infrastructure of hydrogen-powered drones, which thanks to its properties can operate in heights where it's not disturbing for animals or animals living in the forest. This infrastructure can transmit announcements about dangerous animals like bears moving around certain routes or close to the houses of people. This infrastructure, however, does not just protect just human well-beings, but also endangered species, and we can also mark territorial zones where young animals are born. It can map as well the origin of different dangerous animals, bug beetles, as well as mosquitoes around houses. We can use rescue drones. This drone bears some antidote to a person that was hit by a snake. We have a rescue team, but we have also these drones that can transport the entire rescue teams, but also rescued people. This infrastructure in the mountains can work also in a case of avalanche, during disasters as floods. Autonomous aircraft can be applied and evacuate a huge number of people from these zones. Our vision is to support humanitarian support for these purposes. We have the network of big aircraft drones, which are hydrogen-driven, hydrogen-powered. Also, how we deal with how to help the urban infrastructure, how to transport people, decrease emission, improve the living conditions in the cities. VTOL aircraft can land on the roofs of buildings. We can have zero emissions at any time without disturbing people in populated areas, and can get to people based on a phone call. And if there is a surpass of in renewable energy, we could store it and stabilize the electricity network. Our vision of hydrogen-powered island, where we get it from wind and solar panels. Subsequently, we store it in vessels from which we tank that into the aircraft. By connecting these hydrogen-powered islands, we create the entire hydrogen-powered valleys and extend our hydrogen-powered system. We can deliver different types of loads for humanitarian, but also commercial purposes, and big loads, a long distance of flight and low emissions. This all is a part of our vision as well. Well, we put a load from smaller to bigger packages up to the big container there, which is then brought to the barrier, which is currently our VTOL, and when it's full, it takes off with efficiency of 15. It can fly up within 90 minutes to the next logistics centers. This logistic network consisting of our hydrogen-powered islands can make our transport of material more efficient compared to the ground transport, increasing the energy load, and we have even the low or zero emissions. In mountains, we can use VTOL aircraft for missions in the strictest protection zones of nature. Mobility is sometimes between mountain cottages, and then we can really supply to different cottages, or we can transport people or a load. In our visions, we can see improvement of transport of possibilities for politicians when bringing them to different regions or to short distance flights into other countries. Low emission flights would make this transport more efficient. With this slide, I would like to thank you for your attention, as well as the entire team. And I would like to invite Mr. Uhrik, who will continue with our further challenges. Thank you very much. Thank you, Michal. So I'm coming back to the mic, and I would like to sum up the presentations we've heard today. I would like to conclude this section before the panel discussion that is ahead of us. Namely, with an idea. When we ask people who, for example, operate hydrogen-powered lorries, buses, or even cars, passenger cars, when we ask them why we don't see more cars, these hydrogen-powered cars in the streets, we hear the answer because we lack the infrastructure for these cars. When we ask people who are able to create such infrastructure, who are responsible for that, why doesn't it exist? Why? Because we do not have because we do not have enough cars to create the infrastructure. So this is like the question: what was it first, the hen or an egg? Well, and I get my colleague says it's not like that. We should ask a question, or we should say ecosystem was the first one. Maybe it was not so friendly, not developed, but it was the first one. And when this first island, or we have already the entire eco valley, when we start to build it in a complex way, not individually, separately, but in a complex way, we believe it can be prosperous. We can develop as every well set up ecosystem. This is what we believe in. So our small island, as I mentioned in my first presentation, should include everything. We would like to generate our own hydrogen. We would like to deal with its distribution and test the operation of several vehicles. It's built first in Poprad, Prešov, Košice, where this small island, peninsula, should be connected to the hydrogen valley, which is already existent there. So we are not the first one. We are just developing this ecosystem through another evolution. When this system is set up correctly, as I'm an engineer, I invented such a pictogram. When we set up it correctly, and many engineers know that, these are several elements which, when they are set up correctly and none of the wheels is missing, the middle part, it's called some gear. A sun gear can start the planetary gear that all parts get into motion, despite that the force, the momentum that is created by the small gear or by the small wheel is smaller. And the impact to start its entire operation, of course, can be big. But we have to put a lot of energy into that because the frequency and the revolutions should be high. So individual parts of ecosystem, we talked about vertical takeoff, landing, about smaller, bigger drones, also about different possibilities of storing hydrogen. This has to be supported by the infrastructure where we will have the access to hydrogen, to its distribution that will allow us to start also the operation of individual hydrogen products or a business. So to conclude, if the ecosystem is set up correctly, or what are the conditions for the correct setup of the system? So speaking for myself, it's about the vision. We have to have a clear vision of what we want to achieve, and I think it's been quite obvious from the presentations what our vision is. But so that the vision is fulfilled, the ecosystem has to work, and it's based predominantly on human resources, on a scientific research infrastructure that should be continuously developed and to which we want to contribute. If this ecosystem is robust, it can produce a big number of innovations, knowledge, and business opportunities. Of course, it's an ecosystem. That means it's not a static thing. This is something that is developing in time. Any change is not an obstacle in development of the ecosystem, but an opportunity when the branches of the ecosystem can develop into unexpected, diverse challenges. We do not want to stand on one place, but we want to build a robust, resistant ecosystem, being able to adapt to any changes in the future. By this, I would like to thank all our partners, either from academia, industrial sector, or public institutions. Thank you very much for your attention, and I'm looking forward to further cooperation with you. Thank you very much. In the meantime, we got one question referring to the topics of this block, namely a question regarding energy density that can be expected with the usage of spherical vessels for storing hydrogen compared to cylindrical ones, and maybe lithium polymer batteries, which is a question directed to Mr. Ritter, and I think it refers to his presentation, doesn't it?
Of course, the answers will be in English.
Well, the efficiency of the cylinders is a little bit. It's working. It's a little bit depending also on the pressure level, because these resistance of the materials which we use in the pressure vessels, unfortunately, is not linear. And we are targeting at efficiencies of 10% or better. As Tomasz already said, in this moment, the efficiencies are between 6 and 7, and this is by the market leaders. So that is a very important step, and we are working on that. So please respect, we don't want to make assumptions today. We want to present facts and real results to you after our work is done. Thank you.
Ďakujeme veľmi pekne.
Very much for the answer. Is there any other question related to the topics of the presentations in the blog? If there's no question, I would like to thank you very much for the attention, and I take the liberty to present to you a short discussion which has a large potential to move the topic of hydrogen mobility and its ecosystem further, not only from the point of view of the already presented project, which shows really very interesting ambition, but also from the point of view of wider insights to the overall Slovak economy and its international dimension. So now I would like to ask all the speakers which were already present, and also the new ones. But let's start with Professor Sinai. Feel free. Have a seat. It is not surprising that when it comes to the transportation systems of the future will be discussed by Mr. Professor Stefan Klein. Yes, please applause, because he's the CEO of the air car company, but everything that he has done to contribute to the design of new transportation means few have to say more than him. I would like to also ask Mr. Martin Sedlak, who will be representing the ecosystem, which is created by Proton. From the academics environment, I would like to ask Mr. Hlinka, who is the Dean of the Faculty of Engineering from the University of Brno, and also from the scientific field, but from a different area, because we also need to take a look where we will take the hydrogen from. So I'd like to ask Ms. Kotulova from the Slovak Academy of Sciences. Feel free, the floor is yours. Maybe the first question we shall start with, from the point of view of the future operation of the ecosystem, is the question of the infrastructure. I take the liberty to say that we have the youngest stakeholder in this panel and the leader of the Tomark Proton. How do you see the position of the project which you lead in terms of the development of hydrogen ecosystem in Europe? And this is also the question related to the infrastructure, which is very important. During the preparation of the project, we managed to persuade the European Commission that we not only need to be developing the transportation vessel or the transportation means, but we also need to think about the storage tank. And we decided that there should be all the infrastructure parts on the roof, and also the storage tank and the pump. And therefore, within this project, we'll have the pilot project as the small beginning, and we will be able to connect this island to another one. For example, in Košice self-governing region, we have the hydrogen valley. So this is the way how to start, starting from the small island and later on to interconnect it with another one. Island with another island will create a network. This is not our idea. This has already been operating successfully in Netherlands. The next question is focused on the core of the development of mobility itself. What we see on one hand is the trend of decarbonization of mobility, but on the other hand, yet at the same time changing the substance of all the flying engines, flying machines, is the hydrogen ecosystem, and we also influence the way how we steer these machines. We should maybe also be speaking about the autonomous steering. So let me ask you, when it comes to the design and the vision, I would like to ask Mr. Sinai and Mr. Hlinka, how do you see it in your areas of operation, Professor Klein? Well, I'm an active pilot, so I'm flying on the current airplanes, which have been profiled in a short time into various classes. For example, we had ultra low-cost planes. And these are the gliders, and this category is very important also from the point of view of our branch and industry, because Slovakia used to be a country without any own airspace industry, but after the division of Czechoslovakia, we didn't basically have anything. But what is important to say that in short time, we have 6 producers of airplanes, which is a unique fact. And one more note, this happened without any substantial state support. All these people were enthusiasts who were working in their garages. Basically, this is an example of Tomark as well. So I think that the future will be connected with this category, and those airplanes that are already existing, the development is really heading forward in a very fast pace. For example, airplanes can already be put to emergency modes where they can land themselves. And I think that the future will be connected with an alternative, and there will be way more alternatives than we have today. And this very ambitious project we see today has the DNA of searching of new paths. The presentation was really very interesting also for me. Thank you. I think the approach dealing with intelligent modules will basically be speaking about the right thing, that for the right purposes there will be the right vehicles. Well, we see the collaboration of airspace and autonomous steering, and also hydrogen. In all these areas we can see a huge leap forward. Maybe we're a little bit more ahead in the autonomous steering, and we will be not seeing autonomous airplanes in the short future. However, how these technologies and all these challenges are being developed, I think that we will be witnesses of the huge leaps forward in the technology, be it hydrogen technology or the autonomous steering. So hopefully we'll be meeting each other in a couple of years, and we will see our progress. The academic power of this panel is a very good advantage. Professor Sinai is an academic, but I would like to ask him one very simple question, because he is the person who has been with the hydrogen industry from the very beginnings. And I would like to ask you, from the point of view of airspace transportation, the airspace industry is considered to be one of the biggest producers of emissions, and the objective of this project is to decarbonize economy and its areas. How does the environment, I mean the legislation, regulation authorities, and other regulatory environment being created by the authorities, how does it affect the whole situation? Because for such a complicated area like airspace, we need to align the legislation which should be defined by the authorities, or is there also room for companies or innovative stakeholders for other areas to also move with this regulation? Hopefully my microphone works. Thank you very much for the question and also for your kind introductory words. I'm very happy that I managed to start this hydrogen topic, even though I was dealing with the theory of risk and also what my colleague Klein has been dealing with. We have known each other for a long time. He also had some failures in his business, and I feel sorry for it. It was really something of a breakthrough technology. But me personally can say that after these 3 years, I had a great feeling today. There is a project, IPCE, which is being observed by the European Union and which could and definitely will be partially original, not only in terms of Slovakia, but also in terms of the conditions of the European economy sector. Maybe I only misheard it, but I don't know how many people they have already addressed with the project, how many people they already have, and with how many they have already communicated, be it the storage tanks or other aspects. It was already mentioned that we have BMW collaboration. We have been in this hydrogen experimentary lab, and you know, if such a company is searching for Prešov city, which is really a great presentation of Slovakia and many times way better compared to some Brussels diplomatic forum, obviously, in order to be successful, and I feel myself to be a part thereof, I already believe in potential of these people, because the very essence of a project is the people. You can have money, you can have hardware, you can have other things, but if you don't have the brains, you will not be able to move forward. And I was already taking a look at the audience that really collaboration with Tomark is a security that it will be successful. When it comes to communication with the Ministry of Economy, I'm only being an advisor. If I want to advise, I do so. If I don't want to advise, I don't. But mainly European money. European funds are here. They are present, but really you need to be very active in order to be able to attract these European funds to this project. Based on the number of the presenters, how much it already costs you from your own pocket. But I don't want to be saying this. If the objectives are large, we do not take the barriers into account. And Professor Klein knows the most about this. One more view of an airspace engineer, the question who should be deciding and who should be drawing the development forward, whether it will be the legislation maker or any agency or national airspace regulations office. So I think this should be a collaboration of all these three partners or areas, because we already see in Europe that one of the future fuels will be hydrogen, and this is because there are huge teams developing solutions based on hydrogen for the airspace. For example, it could be Tomark Proton for the smaller airplanes. Airbus is also very ambitious in the larger airplanes. So the legislation is already being prepared. At the same time, the teams which deal with the development of new solutions will sooner or later have to communicate with these regulatory offices if they want to introduce hydrogen as a fuel. They will have to communicate this because the regulatory office will communicate this from the point of view of the current standards. But at the end, this will show us how the future technologies will look like, and also regulations after 5 or 10 years after this will go into practice. Just a short note, you probably do not know how we deal with these things in Slovakia. We have an overview of, let's say, 900 technologies. We are making an overview of the regulations. And the next step will be that we will consult this with the Transportation Office, Ministry of Transportation, because this is an area, just like you have already outlined, it is our obligation to create conditions to do so. We have also very good contacts at your Ministry of Economy and Industry, and we will search for synergic effects in order not to reinvent the wheel, because for many, many years we used to be one country. Hopefully we'll find this synergy, and hopefully that we'll also be taking a look at other areas and take a look at the norms and standards which could be also applied at our area. Of course, the good thing is that there is this pressure from the lower side, from the below, which creates pressure to the upper side. One more note, when it comes to this project, we have seen many levels of the project, the level of prototypes, creation of the drivetrain, which uses hydrogen, but maybe something was omitted. And the thing is the people. We do not have enough people in order to have aerospace construction in our universities. And I think this is a very good opportunity to create the pressure that one of the technical universities should have a specification, special area for 5 or 6 students, just like we saw it on the presentations. We really should have such a department. We have universities in Žilina, in Košice. However, these are oriented in a little bit different way, maintenance. But I think that the construction is of key importance in order to start something new. I think this was a very strong message of this discussion. Before we start with the overlapping of these topics to the practical development, let me point out one area where we could use the skills of this panel or the knowledge. And this is the first event, as far as I can remember, when it comes to the Slovak hydrogen power. And nobody has ever asked at this discussion where we will take the hydrogen from. But I think it's good that the Slovak science does something in this area. Let me pose this question to Mrs. Kotulova. Because we see that the area of natural hydrogen, which is being observed by many countries, this starts to be interesting because unlike any other produced hydrogen, the common factor of hydrogen is high energy requirements, but the natural hydrogen is a renewable source if we are able to find it. What are the activities of Slovakia in this area? Thank you very much.
The official activities, well, we don't have them where the French or Belgians, the Germans, Brazilians are. They already have a pilot project. They efficiently search for hydrogen, natural hydrogen. As you said, it's the greenest one, the cheapest one. It's 10 times cheaper than hydrogen produced by well, Slovakia, unlike those countries, has not started yet. And so far, we haven't developed a special methodology how to proceed with the research of the relevant country or with the structures. So in this stage, it's up to the research scientific institutions, universities to develop something like that. Despite all that, in our leisure time, we looked at this issue. We found several locations in the 1960s, where some bores were for hydrogen. We found the content of 65 that was analyzed, and these locations are not far from Trnava or Vienna or close to Bratislava. Some indications come from the eastern part of Slovakia. We know in France we have a huge boom in terms of natural hydrogen in the northeastern part of France, where there is a coal location. It's not mined anymore. It contains a siderite mineral, and they found out that the deeper they go to the depth, the more hydrogen is contained in water. This system is also in Slovakia, in the eastern part, where we have the anthracite mine, old one. The same minerals can be found there. Besides, next to the production of natural hydrogen, we have actually iron contained here. We have closed iron mines which have been flooded with water. You could see the ecological disaster where red water escapes. It's full of iron. It's up to us to be able to adapt these reactors to our needs. We can't, of course, expect huge sources of iron. As Professor told me in the first lecture at the university, Slovakia is a country rich in poor locations of minerals. So this is what it is about. We should look at what is in our storage room. So we could connect the islands to use what is available to us. So I would like to appeal to what I saw in France. The state, the country doesn't support just the geological system as it's found underground, but we know these are also small locations, and we can look at which production to start there. We can help where to store this hydrogen, namely big capacities. We have some locations in the eastern part of Slovakia. Within another project, we stored hydrogen into salt locations. Well, it's a recommended method. Bigger volumes do not have to be put into tankers. But if you want to, for example, produce blue hydrogen, we can use methane. We produce CO2, but we can advise you what to do with that, how to store it. So we can advise you where there is the source of hydrogen, or where we can start it artificially to start the reactor to generate hydrogen. We should be able to connect those places and increase employment and build such islands, actually. You've mentioned many interesting areas in terms of scientific disciplines, but also in terms of decarbonization. I hope I'm not the only one in the room asking the question, which qualifications or scientific disciplines are engaged in these areas that you have mentioned? Through development of which areas we can help that? First of all, this is the basic research, the fundamental research, because these are new things, decarbonization or this hydrogen. This is just 5 to 6 years old. And of course, we would have to invent a kind of a method to efficiently search for the locations of the sources of hydrogen. And then we have geotechnical labs, technicians, different skills, professions connected to geotechnology, and of course then technology itself. Let's say, well, it's important to stay at places where hydrogen is generated so that we do not have to transport it through pipelines or systems. So we should localize the source, and there on the side we should use the systems. Slovakia is rich in geothermal system. This is quite unique, so the temperatures of these systems could help us start the generation of hydrogen from underground. So a number of geological, geotechnical things. The next one, the next question is refers to the return of investment. But I think the question is in what way the environment, the public institutions or organizations, how can they support the development of such projects in Slovakia, bringing the benefits, starting with such areas, ending up with composting. I would like to ask, well, we can support it by finance, of course, funding, because we need a big capital for that. But what else, especially in the area of knowledge-based capital or knowledge of people, what other areas next to the R&D, what could help these projects to attract capital to Slovakia? Mr. Sedlak leads one of these projects, but I would like to hear the answer from Professor Klein. I think the state is important here through the Ministry of Education. I mean, the university area, the academia is has lack of finance in aviation. There are a lot of steps ahead of us. In the Czech Republic, they have an aviation testing center which helps the advancement of the aviation. In terms of intellectual side, not all things, well, commercial from the beginning, but the dialogue between the industry and the schools. For this purpose, the institutions are extremely important. So fingers crossed for this project, because so that these projects are start. We have such projects abroad in VTOL projects, but this is built on enthusiasm. If these people are not pilots, enthusiasts that like working in this area, it requires a lot of personal engagement. It's difficult to compare this field with other branches. From my experience, the existence is important. So the first condition is being fulfilled, that we have manufacturers. And the next step to make, there is a next step to make. In designing cars, for example, we had we built something like that in 1992. We asked the question, why do we need design for such a small country in designing cars? Mr. Uhrig was a former director of Volkswagen at that time. He said, I would open the door for you, but you have to take care of the other things, all other things. And this is how we started the enthusiasm. And BMW designers from our school, I saw one graduate of our school here as well. So we can see the fruit of this hard job. And this knowledge-based environment at university is extremely important. And aviation is a very comprehensive area. Thank you very much. Mr. Sedlak, your view from the entrepreneurship area, from the perspective of your colleague who have been presenting here today. When I come back to the origin of the question, what is more important, the politics or economy, the companies? From the holistic point of view, from what we've learned recently, we can evaluate that the politics matters most because they create the playground, where we can bring the sand, the toys, and only then, when businessmen then have a good environment, they can play. And I think this is how it works. When we started with the project, one of the first things is that Daniel Older, of us too, he said a holistic point is more important. Before we start, let's go to the universities, let's plant the seed, let's search for the talents. And it has proven to be the right thing. Today in the project, we have more students who study here or abroad, and they are successful because the cooperation between the politics, the state organization, between the companies has to reach up to the universities, which is alma mater, where further generations are educated. This is the potential, the enthusiasm that has been mentioned here, which is sometimes too courageous. Then it has to be combined with seniors, older colleagues who have experience, and they can cultivate that to something that is more effective but still safe. Thank you very much. The question I would like to ask now is the question to Professor Sinai, namely, what is the potential of such projects to transform economy to a higher level or in terms of engagement of innovative knowledges or innovations or inventions, because this area has been viewed recently. We have industries like machinery, and now in the past decades, automotive industry, which is cross-cutting. But we said this have to be big companies, production companies that will bring their R&Ds here. But can we put pressure to the change of viewing such smaller projects, which address the same areas as automotive industry, but can they bring something new into the system to change the economy? Well, Martin, you know what I will say, because we have known each other for several years. Definitely, absolutely, yes. Let's call it as we wish, but these are exactly the nests where the new ideas are born, which are not loaded with anything. If we have a new company and we expect it to bring a new R&D center, you are wrong. Only my friends are lucky enough to have Skoda here. Yes, but we saw Volvo manufacturing company. And we asked the question, well, where will the R&D be? In Nitra, first answer. But then when they developed, it was in Budapest. So this is not a good way to rely on it. Let's take US Steel, Nippon today in Košice. They basically do not have their R&D here. They had just testing of metal or sheet plates. So I'm almost convinced of these steps. Either it was Mr. Professor Klein, Tomark, or our friend and close to Žilina. Well, we have a lot of them. Those should be those ones who should be supported, not just verbally, but so that from these companies we see these companies are developed into commercial ones. I've asked the question, how many professionals does Martin have? He didn't tell me the exact figure. I was quite surprised that they have such a huge number, and I said, well, you have to pay them. So again, it's about finance. If you say it's not important, the funds are not important, they are only at the first place. So there is nothing else than to use my effort so that these companies are supported. But ladies, gentlemen, I would like to invite you to do an efficient marketing for hydrogen technology. Everyone should do his job on their site. When you presented white hydrogen, I said, well, I have to visit you at the university, but well, I heard your lecture, but you can. We met here today, so we have geological source in Slovakia. It won't be today or tomorrow. We will produce it artificially today and tomorrow, but the rest can be done. And there are a lot of people here, either my friends from Košice region. The valley is working, and the potential of connecting of Tomark with them, this is functioning already. We have such examples here. What we miss here, or what we don't have here, we don't have a huge support from the government. And the reason is quite clear. Slovakia has energy issues and other issues. But I would like to motivate you in the program resolution of the government. Energy is point 4 to fulfill or develop the ecological ecosystem, fulfill the action plan and innovate it and continue with all activities in energy, also in this direction. So it's a political document, government resolution or declaration. So we could say, oh, government manifesto, we could say, we could forget it, but we can't. The last day before the election, politicians are very sensitive when it comes to the evaluation of the government manifesto. So it will be your and my job to engage and ask from them everything what we've heard here today, because we are just a small lady, or we are not influential enough to have an impact on that. We could see a film about hydrogen produced by CVTI. Originally, it was supposed to have 45 minutes, a beautiful film, but it was shortened to 22 minutes. What is our job? To get the original version and ask a question, why couldn't the people see that in a full version? So I think this is an important job, and we have at least two concepts here. One is just purely a hydrogen concept. When Professor Klein comes home, I think he will ask a question when taking a bottle of wine. I will start with thinking about hydrogen, and at least we will get one more person who can evaluate the pros and cons of hydrogen.
Just a short note that the structure of industry is changing a lot, and this helps the smaller enterprises to come to the finals, because we were used to the situation that there were only larger companies. So what we see and what we hear from the politicians about knowledge-based economy, we should deliver already. And really, the education is of essence. I, for example, have 5 people who work at a prototype, and it was done by 5 youngsters, 5 PhD students, which are under 30 years of age. And we already have 3 our graduates. So it is possible to be competitive in a smaller team, and this is the main change. Let's just commercialize it, help these projects with marketing, and the difference, as it was properly commented on, we speak about the automotive plants which have plants here, but the Škoda is the car maker itself. This is why they have the development, and our task is clear. We should help the other brands which are not from the abroad, but which are Slovak, for example, Tomark Proton, or any other intentions under the auspices of other companies. And this is a good thing to say. And I would like to ask the final question to Mr. Sedlák, and the question is as follows: how would an hydrogen ecosystem look like, not only in the Slovak environment, in which the Proton Tomark could be developing properly as a company? You know, I think that we are taking a little bit too holistic view on the world, and we are searching for the resources where we will take the hydrogen from. So we go from the very beginning, because most likely the price of the hydrogen will decide whether this is feasible. So on one hand, we have windmills, solar panels, nuclear energy. At the same time, we see huge development of nuclear fusion. What has happened during the last year is a really huge leap forward. So each of the countries have certain specifics which they could use. We could have this so-called white hydrogen. Another thing is the support of the political parties, which is of essence. Our experience is a little bit different. If you study the rules and the legal regulations properly, and if you collaborate with the given institution, for us this is the Ministry of Economy, then everything is feasible. So these are the main attributes. So how the ecosystem should look like is quite clear. We should only start with it the right way. I would like to comment on these last words, that our voices are not heard properly, but the area is really very interesting. Thanks to you, and I would like to thank you for the presentations and for the discussion. And one more applause for the Tomark Proton project, which shows us that from what only looks like enthusiasm can really emerge very concrete ideas. So one more applause for Mr. Sedlák and his colleagues. And I would like to thank you very much for your attention. I hope this was interesting for you, and I would like to invite you all for the lunch, and I would like to wish you to enjoy your meal. Thank you very much again.